Hello. So we have already started our discussion on phenols. We had discussed a few reactions of phenols also, especially the Fry's rearrangement is what we had discussed. In this session, we'll be discussing about the Claisen's rearrangement, then Elb's persulfate oxidation and the other reactions and their mechanisms. What is this Claisen's rearrangement is what we'll see first. Claisen rearrangement. Clason's rearrangement involves the heating of allyl ethers, okay, at a temperature of 200 degrees Celsius. So when allyl ethers are heated about 200 degrees Celsius, they undergo intramolecular rearrangement to form orthoallyl phenols. Okay, so allyl ethers when heated at 200 degrees Celsius undergo rearrangement intramolecular within the molecule. They undergo rearrangement to form orthoallyl ethers, orthoallyl phenols. This is Clason's condensation rearrangement. For example, protyl phenyl ether on heating gives orthomethyl allyl phenol as follows. Let's take a reaction. Okay, I have an ether O CH2 CH double bond CH3. This is an allyl ether. The name of this is crotyl phenyl ether. When this is heated, when this is heated, this ether undergoes rearrangement. This ether undergoes rearrangement to give orthomethyl allyl phenol. Okay, this is what you are going to get. We'll see the mechanism later. So this is what you are going to get. This will be phenol OH. This whole group migrates to the ortho position. Okay, on migration you get this compound CH double bond CH2 CH3. You get ortho methyl allyl phenol. That's what you get. Okay, let us discuss the mechanism of this, how the reaction takes place. Okay, very important reaction. This is mechanism. Benzene O CH2 CH double bond CH CH3. Okay, this molecule only. O ether, carbon oxygen carbon bond. O CH2 CH double bond CH CH3. When it is heated, what happens is here. This electrons attacks here. Okay, this double bond moves here. The bond breaks. So what you get? You get this compound. Okay. There is no double bond here because the attack has taken place. You get this compound. Okay. This electron moves here. Double bond O. This has attacked this carbon. Why it will attack this carbon? Because there is double bond here. So it will attack here only. So when it attacks this, this moves here. Okay. So what you will get is here. Carbon, benzene and this carbon bond forms a bond. So you get a CH this. Okay. So this group will be attached here only, CH3. So this benzene ring, benzene carbon attacks this carbon. So there is a bond between these two. So this is the CH that is attached here. Okay. Next, we have CH, this CH, and then we have CH2. Okay. The double bond has shifted here. Look at this. This is what you get. Okay. Now, so this will be equilibrium in this compound. You will be having an hydrogen here. Right? You will be having an hydrogen here. So then what happens is the loss of hydrogen proton takes place here. H. This goes here. Double bond O becomes O minus. The H plus that is lost here moves here. So you get this. The electron moves here. So you get a double bond here. Then OH, CH, CH3, CH, double bond CH2. This is what you get. Okay, this is the Clason's rearrangement. Okay, so allyl phenyl ethers when heated gives you allyl phenols, orthoallyl phenols. This is called as Clason's rearrangement. Okay, now next reaction. Another very important reaction is Alps persulfate oxidation. Alps persulfate oxidation is another reaction. This is a reaction to convert monohydric phenol into dihydric phenol by treating phenol with potassium persulfate in alkaline medium. Okay, this is the reaction which converts a monohydric phenol. Monohydric phenol means phenol containing only one OH group. These are called as monohydric phenol. Converting this monohydric phenol into dihydric phenol. With potassium persulfate, K2S2O8. Okay, in alkaline medium. Okay, so this phenol, this is phenol. Right, now in this reaction hydroxylation takes place usually in the para position. So OH comes at the para position. But when para position is blocked, it would be at ortho position. Para position, if it is blocked, then the hydroxylation will take place as ortho position. Let us go for the mechanism of this. Okay, so what happens is here we have a phenol. Okay, phenols are in presence of a base. It will be O minus only. Phenate ion will be present because phenols are acidic in nature. It is a basic medium. OH minus will take up this H plus to form water and you get a phenate ion. Plus what we are adding? We are adding potassium per sulfate is what we are adding, right? So potassium per sulfate. Look at the potassium per sulfate, how it will be. There will be oxygen bond. There will be SO3K. There will be another SO3K. Potassium per sulfate. And what happens is here? A phenate ion. This moves here. This electron moves here. This electron attack the oxygen. So attack takes place at the which position? Para position. Okay. So you get this compound. I'll just write the structure of that compound. So there is a ring here. The electron has moved here. So double bond O. This electron moves here. Double bond. So the double bond that is already present here. This double bond. This electrons have attacked this. Okay. So you have an hydrogen here as usual. So this electron have attacked this. So a bond between this carbon and oxygen will take place. Okay. Now, so when the attack takes place to this oxygen, this bond breaks because oxygen can form two bonds. So it is forming new bond. The older bond will break. Oxygen bonds are generally weaker. They break out. So what you get? You get this compound, that is O SO3K. Okay, this is what you get. Okay, and intermediate is formed. This is the intermediate that is formed. Next, what happens is here. Okay, the proton loss takes place. Okay, this loss of proton takes place, and the electron moves here to form a double bond. This electron moves here, and this electron move here. You get this compound. So the loss of proton, aromatization takes place. This is the ring. This electron move here to form the double bond. This electron move here. This electron as usual. Double bond O becomes O minus, and we have O SO3K. 3K. Okay. Then on acidification, H plus and water. Okay. On acidification, what happens? You get this compound, benzene, OH plus KHSO4 is what you get. So you get a quinol. This is what generally happens in an Alps persulfate oxidation. Okay, a monohydric phenol is converted into dihydric phenol by using potassium persulfate in a basic medium. Okay, now, so these are the two important reactions that are there. Okay, so let us move with another reaction, that is Lederer-Manasse reaction. Okay, another important reaction that is called as Lederer-Manasse reaction. Let us see what is this reaction. Okay, let us try to find out what is this reaction. Manasse reaction. This is a reaction between phenol and an aldehyde in an acidic or a basic medium to form condensation product. Okay, this is a reaction between phenol and an aldehyde that takes formaldehyde, H C double bond O H. Okay, in acidic or a basic medium, the reaction takes place in an acidic medium or as in a basic medium to form condensation product. Okay, important example of this reaction is the phenol and a formaldehyde reaction to form para-hydroxybenzyl alcohol as the major product and orthohydroxybenzyl alcohol as the minor product. So this is what you get. OH, here you get CH2OH. So this is para-hydroxybenzyl alcohol. This is a para product. And you are getting orthohydroxybenzyl alcohol. Ortho product. Right? This is what happens. Okay, phenols when treated with formaldehyde will give you para-hydroxybenzyl alcohol and orthohydroxybenzyl alcohol. So reaction may be acid catalyzed or reaction may be base catalyzed. Let us look at the reaction. Okay, now let us see this. Acid catalyzed reaction takes place in the following step. First, let us go for the acid catalyzed. Acid catalyzed. Right now. So what happens is, in presence of an acid, first protonation takes place. HC double bond OH. In presence of H plus, protonation takes place. Okay, C double bond O, the protonation takes place here. Okay, the electron move here and the protonation takes place. So you get this compound, that is HCH OH. This carbon will be positive charge. See, the lone pair of electron attacks here, the electron move here and the attack takes place here. So double bond O becomes OH. So this carbon loses electron, it carries a positive charge. This is what you get. CH2OH is what you get. Then as usual, an electrophilic attack takes place. Okay, an electrophilic attack takes place at ortho as well as the para position, but para-hydroxybenzyl alcohol will be the major product and this ortho-hydroxy will be the minor product. Okay, generally what happens, so the attack takes place as ortho as well as the para position. Let us see it. So next step will be, this is the first step where protonation takes place. Second step is electrophilic attack takes place. Electrophilic attack takes place. Okay, so now electrophilic attack means what happens is here we have phenol. Okay, we have this electrophile that is generated, that is CH2 plus OH is what we have. So this electron attack here. Okay, now when this attack takes place here, these electron they move here to stabilize this. Okay, the electrons of this, the shade between these two carbon move here, so the electron moves here. So what you get this compound, that is double bond OH plus, and you get this CH2H and then hydrogen. Then loss of this takes place. OH CH2H. So ortho-hydroxy phenyl benzyl alcohol is what you get. So this is acid catalyzed mechanism. This mechanism takes place in presence of an acid. So similar product is formed if you use a base also. So let us see the base catalyzed reaction. What happens when you use a base? Base catalyzed reaction. Same reaction, same product, that is Lederer-Manasse reaction. When a phenol is treated with a base, I mean with NaOH, you get sodium phenate first, because phenols is acidic, NaOH is a base, so acid-base reaction takes place initially. Then what happens is here, phenate is formed, O minus, we have HC double bond OH, this electron move here, attack takes place here. Double bond O, attack takes place here to this carbon, so it will be CH2 O minus and H. CH2O minus and H. Toss of proton. O minus CH2OH. Okay. With excess of formaldehyde, hydroxylation takes place at both ortho and para position. Okay, now hope you got this. So this is Lederer-Manasse reaction. In presence of acid as well as a base, you get the same product. So even attack may take, same mechanism, attack may take place at the para position also. Now, next one. Next is a synthesis of, a very important synthesis, a synthesis of N-hexyl resorcinol. N-hexyl resorcinol. N-hexyl resorcinol can be prepared by Fried's rearrangement using resorcinol and N-hexanoyl chloride. Okay, hope you know what is a Fried's rearrangement that we had discussed in our last session only. So this is resorcinol. Resorcinol is a dihydric alcohol where the OH group is present at a meta position with respect to another OH group. When it is treated with N-hexanoyl chloride, CH3, CH2 4 times COCl. What happens is here? This is C double bond OCl. So N-hexyl resorcinol can be prepared by Fried's rearrangement. So this is resorcinol. This is N-hexanoyl chloride. So what happens? This oxygen attacks this carbon. Okay, this oxygen attacks this carbon. So Cl goes off. So you get this product. We have benzene, OH. This oxygen contains lone pair of electron. It attacks this oxygen, O, CO, CH2 4 times CH3. This is what you get. Then in presence of AlCl3, and when it is heated, so migration takes place to the para position. Migration takes place as the para position. You get this. This is Fried's migration is what we call it as. Okay, you get OH. This group migrates. You get C double bond O, CH2 4 times CH3. This is what you get. Okay, when it is reduced with zinc, amalgam and HCl, it is Clemenson's reduction. C double bond O gets converted to CH2. You get this compound OH, CH2, CH2 4 times CH3. Okay, this is N-hexyl resorcinol. N-hexyl resorcinol. Okay, this is the preparation of N-hexyl resorcinol. So we do come across another important synthesis that is there for a syllabus. That is synthesis of picric acid. Synthesis of picric acid. Picric acid can be generally prepared by using phenol. Picric acid, that is 2,4,6-trinitrophenol. It can be prepared by treating phenol with fuming nitric acid. That is HNO3, H2SO4. So nitration takes place at ortho as well as the para position, plus 3H2O. So this is picric acid, 2,4,6-trinitrophenol. 2,4,6-trinitrophenol. This is the preparation of picric acid. Okay, so this was about your phenols chapter, students. Before that, let us discuss the uses of N-hexyl resorcinol. N-hexyl resorcinol is an antiseptic, okay, that is used to cure hookworm disease. It is used to treat urinary disorders. The uses of picric acid is, it is used as an yellow dye for silk. Okay, it is used to produce explosive like melanite. It is used in qualitative analysis, okay, to identify where picric derivatives are used to identify the aromatic hydrocarbons. Okay, it is, the derivatives of this compound are used as a surface anesthetic for the treatment of burns. So this was about the phenols chapter, students. Thank you.